Hello guys, welcome back to another episode of Let's Learn Computer Science. Haven't uploaded in a while, and today's going to look a little different. Purely because of the content of these new classes, this is going to be discrete mathematics using the modulus operator and encryption and decryption, and converting numbers to different bases and stuff. So I opted for this notepad kind of POV version so that you can see, oh, look at the shadows of my hands. Yeah, so you can see my thought process and writing it out as I go. So let's start with these first questions. It says determine x div y and x mod y for each pair of the values below. So let's start with this first pair. It's going to be x is equal to 252 and y is equal to 7. So that is our first pair. And if we take 252 with the div operator by 7, this is asking how many times does 7 go into 252. So if we think about multiples of 7, we would get 70, 140, 140 plus 70, which would be 7 times 30, would be 210. And then what are we left with? 42, 42, 6, so 36 would be the answer there. And we can double check here if I do, let's see, calculate. If I do 36 times 7, we get 252. You can see that. I need to charge my calculator. So the answer for this is 36. How many times does 7 go into 52? 36 times. Now I can do x mod y, so let's do 252 modulus operator 7. Modulus is asking what is the remainder after dividing. So since we've already determined that 7 goes into 52 36 times evenly with no remainder, it's just going to be 0. Let's look at another example. When x is equal to 1398 and y is equal to 13. So let's do 1398 div 13. So I can already tell that this is going to be times 100 is 1300. But then we have 98. So if I do 13 times 10, I get 130. So it's less than 10. If I do 13 times 9, I get 117. I guess I have a calculator with me. Let's see. 13 times 7 is 91. 13 times 6 is 78. So it's somewhere between... Oh no, it's 91, isn't it? So if I do 13 times 17, I'll get... 13 times 107? Yeah, if I do 13 times 107, I get 1391. And I can't fit another 13 into there. So 13 goes into 1398 107 times evenly. And it has a remainder of 7. Now the remainder isn't super important for this operator, but for the modulus operator, all I care about is the remainder. So we know that that's going to be 7. So there we go. Now let's see how this operator behaves with negative numbers. If x is negative 21 and y is 33, let's look at what negative 21 divided by 33. Now this is going to look a little bit different. So if I do negative 33 goes into negative 21, this might make more sense if I write it algebraically. So for this example, we had 36 times 7 is equal to 252. For this example, we had 107 times 13 plus 7 equals 1398. Right, these are both for the div operators. So for this one, I could write it as negative 21 equals negative 1 times 33 plus, what is that? 3 and then 9, so 12 plus 12. And we get negative 21. So if we follow this pattern of, oh, this was the quotient, then we can say negative 1 will be our answer from this. So the negatives behave a little bit oddly, but that is how you get to there. And then if we take the modulus with a negative number, I think it's actually easier than saying, if I divide into this, what is my remainder? So what I can do is basically all I do is I say, what is 33 minus 21? And that gives me an answer of 12. So the modulus remainder for this would be 12. Okay. So the negatives do behave slightly differently. And then let's just finish up this last one, negative 457 and y equals 22. So negative 457 div 22. What is that going to be equal to? So if I divide 457 by 22, I get 20.7 and some change. So I know that 22 goes into 457 20 times, but not more than 21 times. 20 times, but not 21 times. But if it's negative, I actually want to go over in the negative, because then I can add the difference with a positive number. So what I'm going to do is 457 divided by 22 was less than 21, but greater than 20. This is kind of the relationship that I have. It's greater than 20, but it's less than 21. So if I want to go over, I'm going to set my factor equal to 21. This way I can write an equation that says negative 457 equals negative 21 times 22. And let's see what that is. This part is equal to negative 462. So I actually want to add 5 so that this equation is equal. And from this I can tell that negative 457 div 22 is equal to negative 21. So that's how many times 22 goes into negative 57, because then I add 5. And then the last one, negative 457 mod 22, we're going to do the same thing. If we subtract these two numbers, we're going to end up with a negative. Where in this one, we ended up with positive. But if you noticed this pattern already, the remainder from the div operator is also what we got when we found the difference between these two. So we can follow that pattern here and say, what was the remainder we got from the division operator? And we can evaluate negative 457 modulus 22 is equal to 5. So there we go. All right, so now we're switching over to the next problem after we've somewhat defined what div and mod and how those operators go. So what I'm going to do is, in the sake of saving notebook paper, I'm going to draw a boundary around there, and I'll do these problems with a red pen. So we need to determine the following value for each of these A through D, and they can be done without a calculator. So 9 times 3 in Z20. So the way that this would be written is 9 times 3, and then you could say in, and then this bold fonted Z to signify positive and negative integers, the maximum of 20. So that's the way that it's typically written, I believe. And all this means is we can do 27 mod 20. And this gives us a remainder of 7. Because you can see 20 goes into 27 once with a remainder of 7. As easy as that. Let's go to the next one here. We have, so that one's done. Let's go on to B. An A there. Oh, this is not 1526. When I copy and pasted it over, it got messed up. This is actually 15 to the power of 26 mod 7. My mistake. But a modulus rule still applies, right? There's no way to calculate 15 to the power of 26 without a calculator in an efficient way. So what we can do instead is take 15 modulus 7, take that whole thing to the power of 26, and then mod 7 that result. So this is a property of modulus arithmetic. So now I can solve for 15 mod 7. What is that? 7 goes into 15 twice to make 14, and then there's 1 left over. So I actually have 1 to the power of 26 modulus 7. And 1 to the power of 26 is just 1, and 1 mod 7 is just 1. 7 cannot go into 1, so the remainder is just what's left over, which is 1. Let's look at the next one here. Let's box that out. So for letter C, we have 352 times 407, in parentheses, mod 50. So we could multiply these two together, or we could institute another property of modular arithmetic. And if you have a factorable number here, you can split them apart and modulate each one of them. So let's do just that. Let's do 352 mod 50. And then since we're multiplying here, we're going to multiply 407 mod 50. Right? So we've rewritten it as this, and then that's just this part. So now we still need to include the mod 50 at the end. So let's see what this is. 352 mod 50. Well, 350 is a multiple of 50, so the remainder is just 2. And then 407 mod 50. 400 is a multiple of 50, and the remainder is 7. And then that mod 50. So 2 times 7 is 14. 50 does not go into 14, so the remainder is simply 14. And that's that one done. And the last one for this example, let me see if I can scooch this up a little bit. Last one for this example will be D. So for D, we have a very similar sort of situation where we have 13023 plus 45052 mod 10. And the same basic rule is going to apply, where we can rewrite it like this, and we just keep the operator in the middle. So instead of a multiplication sign, we'll get an addition sign. So let's rewrite this as 13023 mod 10 plus 45052 mod 10. And the whole thing is going to be mod 10. So now let's simplify the stuff inside of the parentheses. 13,023, 13,020 is a multiple of 10, so the remainder is 3. And then we're going to add 45,052. Well, 45,050 is a multiple of 10, so the remainder is 2. So we have 3 plus 2 mod 10. 10 does not divide into 5 evenly, so that is going to be the remainder of 5, because that's what's left over. So those are those 4 done. Some properties of the modulus operator shown there. Looks like this page is full, so we're going to flip to the next one. All right, so next we're being asked to do a couple of things with each of these pairs. Firstly, we need to find the greatest common divisor, Next, we need to write the greatest common divisor as a linear combination of x and y. And then lastly, we determine if the multiplicative inverse exists. And if it does exist, then find it. So the greatest common divisor is going to be what is the largest number that is a factor of both of the numbers. So for instance, if I had 10 and 20, the greatest common divisor would be 10. If I had something like 42 and 49, the greatest common divisor would then be 7. You see. So there is a good way of going about this, and that's by writing each number given, the pairs given, in their prime factorization. And then multiplying the common ones. So let me demonstrate how that will look. We'll start with x equals 45 and y equals 55. So if I want to represent these as their prime factorization, I can write x as, well, 45 is 15 times 3. So I know that there's a 3 in there. And then I'm going to multiply it by 15. Now, 3 is a prime, but 15 is not a prime. So I can break the 15 down more into a 3 and a 5. But now I have 3 times 3 times 5. So let me write that out. 3 times 3 times 5. These two 3's can be mushed together into 3 squared. So 3 squared times 5. That is the prime factorization of 45. Next, let's do y. That would be 5 times 11. And 5 and 11 are both prime, so we're done there. So now we can compare the values of the prime factorizations of both numbers. I have a 3 squared here. I have no 3 here. I have a 5 here, and I also have a 5 here. And then I have an 11 here, but not an 11 for x. So what I do is I compare all of these. I'll say x has 3 squared, it has 5 to the first power, and it has 11 to the 0th power, right? There's no 11. Y has no 3's, it does have a 5, and it does have an 11. So now we're going to look at the pairs of all these and pick the ones with the lowest exponent. So for 3, y has none, so the lowest exponent is 3 to the 0, which is just 1. So I'll write 3 to the 0. And then I'm going to multiply the lowest of these two. Since they're both the same, we just choose the one. And then lastly, we have 11, and x has no 11 powers, so that's just 11 to the 0. So I wrote them out as the base to the 0, but you can just completely exclude them because you're multiplying them, and the 1 doesn't matter. So this whole thing is equal to 5. And what that tells us is that the greatest common divisor of these two numbers is 5. And that checks out. 45 is a multiple of 5, it's 9. 55 is a multiple of 5, it's 11. So that is going to be the first part of our answer. That is part 1 here. Next, we're going to find the greatest common divisor as a linear combination of x and y. So this is when we institute the extended Euler's formula, I believe it's called. And this is very simple. We just use mod and div. Well, we mainly use div, but we also use mod. So I'll show you how to write it out. So the first thing you do is have your values here, x and y. And what you can do, this equation will be written as x minus x divided by y, or the division operator, multiplied by y equals whatever. This will technically be your new value. So I'll write that as an r. So we're going to do this through multiple iterations until we get to 0, and then we'll be done. So with this new r, it actually replaces the y, and the y replaces the x. So I'll draw these arrows, but I'll write the next equation so it makes sense. So next we'll do y minus y div r times r, and that will equal a new variable called s. And then we swap them out. So now r minus r div s times s equals q. So you can see this swapping of variables. So I'll do this one more time just for the sake of clarity. So this becomes s minus s div q times q p. So this is kind of the pattern we will follow. And this is also a way that you can solve for the greatest common divisor. It will actually be the equation right before we calculate the last one, which will become 0. But this is a process of how you can represent it as a linear combination of x and y. So let's start with plugging in our values. Let's do 45 minus 45 div 55 times 55. 55 goes into 45 0 times. So this is going to be 45 minus 0 times 55. So this is just equal to 45. And a little trick you can do with these is you can start your first equation with the second one instead of the first one. Because as you can see here, once we do our swap, it's going to be as if we started with the reversed. You see, all the 55s became 45s, all the 45s became 55s. So we could have started off with using 55 in the front, but this is will make it more clear, I suppose. So how many times does 45 go into 55? Well, exactly 1 time with the remainder of 10. So this can simplify to 1. So then we just have 55 minus 1 times 45, and that's equal to 10. Now we're going to replace our values like we did here. 45 is going to, or 55 is going to become 45, and 45 is going to become 10. So let's rewrite this. We have 45 minus 45 div 10 times 10. How many times does 10 go into 45? Well, that's 4 times. 4 times 10 is 40. 45 minus 40 is equal to 5. So there is our greatest common divisor there. We got our 5 now. But we're going to plug this in again. We're going to go here, and we're going to go here. So let's do 10 minus 10 divided by 5 times 5. How many times does 5 go into 10? Twice. So we have 10 minus 2 times 5, and that's going to be 0. And this is when we stop. Technically, you don't even need to do that last step, but it's just good to make sure, okay, I'm calculating this correctly, and it will eventually reach 0. And once you reach 0, the equation directly before that was your GCD. So now what's really nice about this is we have a system of equations of which we can extrapolate 5 to be equal in terms of our initial x and y values. So let's do just that. I'm going to rewrite these equations so that they don't have these div functions in them, and I'm just going to simplify it. So 45 was equal to 45 minus 0. Okay, maybe that one's not important. We can say 10, I'm rewriting this one. 10 is equal to 55 minus 1 times 45. And then I have 5 is equal to 45 minus 4 times 10. And notice how I'm writing, I'm not solving for it. I'm keeping the multiples out in front. So I'm treating each one of these as a variable almost. So now I can start to plug and chug. So I have a 10 here. I have an equation that represents 10 in terms of my x and y values that we started with. So I'm going to plug it in. I can say 5 equals 45 minus 4 times this equation, 55 minus 45. And then I can simplify. I can say 5 is equal to 45 minus 4 times 55. And then I have a negative 4 times a negative 45. So I'm going to do plus 4 times 45. And now I can simplify this to say 5 is equal to, I have 4 45s here and 1 45 here. So that's equal to 5 times 45. And then I have a negative 4 times 55. And this is what we call a linear combination of x and y to represent the greatest common divisor. You see, I've written in terms of my x and y with their multiples, what is the greatest common divisor of them? And if you check this, you can do 5 times 45, that's equal to 225. 4 times 55 is 220. 225 minus 220, you're left with 5. So that is that one. You can see this is a bit of a lengthy process, but that's okay. So I'm going to jump ahead to letter C, because that one actually has a multiplicative inverse. I guess I didn't explain why this one didn't have a multiplicative inverse. In order to have a multiplicative inverse, the lowest common divisor must be equal to 1. And that just means that these two numbers are relatively prime. So that could be something like 10 and 11. Those are relatively prime. Even though 10 isn't prime, it's relatively prime to 11 because they share no factor. So let's move on to this one, C, where x is equal to 39 and y is equal to 44. Let's write this in the prime factorization. So 39 is equal to 3 times 13, and those are both primes. 44 is going to be equal to 11 times 4, but 4 can be factored to 2 squared times 11. So that's our prime factorization. Now we can pair these up. 39 is equal to 2 to the 0 times 3 to the 1 times 11 to the 0 times 13 to the 1. And 44 is equal to 2 squared times 3 to the power of 0 times 11 to the power of 1 times 13 to the power of 0. So now that we have these paired up, we're taking the lowest number of the pairs. 0 is less than 2, so we can cancel those out. 0 is less than 1, so we can cancel those out. 1 is greater than 0. 0 is less than 1, so we can cancel those out. 0 is less than 1, so we can cancel those out. Well, now we have nothing. But what do we actually have? We have 2 to the 0 times 3 to the 0 times 11 to the 0 times 13 to the 0. So they shared no common prime factors. And this is equal to 1. So we can see here that the greatest common divisor between these two is equal to 1, which means that they share no other factors other than 1. They are relatively prime. Even though 39 is definitely not prime, it has factors. 44 is definitely not prime, it has factors other than 1. But they are relatively prime because they share no factors. So let's write this as a linear combination of x and y. We're going to use the exact same formula as we did before, the extended Euler's formula, I believe it's called. And I'm going to swap these so that I don't have to rewrite that first equation that ended up just not being useful. So I'm going to start with 44. If I started with 39, it'd be 39 minus 0. And then I'd just have to rewrite it backwards anyway. So I'm going to do 44 minus 44 div 39 times 39. And that's going to be equal to, this is 1. 39 goes into 44 one time. 44 minus 39 is 5. So now I'm going to replace the 44 with the 39 and replace all the 39s with the 5. So I have 39 minus 39 div 5 times 5. How many times does 5 go into 39? Well, that's 7 times. 7 times 5 is 35. 39 minus 35 is going to give us 4. So now I'm going to replace all the 39s with a 5 and all the 5s with a 4. 5 minus 5 div 4 times 4 is equal to 4 goes into 5 one time. 1 times 4 is 4. 5 minus 4 is 1. And if I want to do the last step, I can say 4 minus 4 div 1 times 1 equals 0. 1 goes into 4 4 times. 4 times 1 is 4. 4 minus 4 is 0. So I can do it that way as well. But now I have a system of equations here where I want to set it equal to the greatest common divisor in terms of my beginning values. So let's rewrite all these equations. 5 is going to be equal to 44 minus 39. 4 is going to be equal to 39 minus 7 times 5. And 1 is going to be equal to 5 minus 4. So now I just have to solve for 1 in terms of 44 and 39 by plugging it in. So the first thing I see is my equation that equals 1 has a 4 term, and I have an equation that equals 4. So let's plug those in. Let's substitute it. I'm going to write it down here. 1 is equal to 5 minus, and I'm substituting in this equation for 4, minus 39 minus 7 times 5. Let's simplify this out. I'm going to get 5, the negative times the 39, so minus 39. The negative 1 times the negative 7. You get plus 7 times 5. Combine the like terms of the 5s. I'm going to get 8 times 5 minus 39 equals 1. 40 minus 39 equals 1. That checks out. Now I have an equation for 5 I can plug in. So I'm going to rewrite that. I'm going to say 1 is equal to 8 times, and I'm plugging in the equation for 5, 44 minus 39, and then minus 39. I'm going to simplify this without actually finding the product of any of these. I'm treating my initial values as variables. 8 times 44 is 8 times 44. 8 times negative 39 is negative 8 times 39, and then I have a minus 39 here. If I simplify that by combining like terms, I get 8 times 44 minus 9 times 39. You can pull out your calculator and check that that is still equal to 1. 8 times 44 is 352. 9 times 39 is 351. We subtract them, the difference is 1. So this is our linear combination right there. But since I said two values have a multiplicative inverse of their modulus operation if they are relatively prime, and we see that by if the greatest common divisor is equal to 1, we can find a multiplicative inverse. And luckily for us, we've done all the heavy lifting, because the multiplicative inverse can be found through the linear combination. So all we need to look at is, we need to find the inverse of x mod y. X was equal to 39, and mod y was 44. So the modulus of this is equal to 39, but we need to find a multiplicative inverse. And I've been throwing that word around, but basically what it means is some number. We already have x and y, so I'll call this s. S times x mod y should equal 1. And this should be in parentheses. This is called a multiplicative inverse, finding s. So I need to find some number multiplied by 39 that when the product of those two numbers is mod 44, it will equal 1. And this is where the linear combination comes in hand. We have to look at the coefficient of the x term, and that will give us our multiplicative inverse. But notice it is not negative 9. We need to find a positive integer, or s is positive. So the way we can do that is by taking the coefficient if it's negative, only if it's negative, really. And we're going to modulus by the y value, which is 44. Now, before we said 44, we said if this number is negative and less than this number, then we can just subtract it. So let's do that. 44 minus 9 is 35. If we do 35 times 39, and then take the modulus of that number, we get 1. So 35 times 39 mod 44 is equal to 1. And because it has this unique relationship, that means 35 is our multiplicative inverse. Let's look at a few more examples here. This is going to be a longer video just because that is the nature of how math be, I suppose. It doesn't have to be long, but it is. So here we're just converting numbers in different bases to decimal form. And if you watched one of my previous videos, I'm pretty sure it was the first video, Intro to Computer Science, that I explained how number bases work and how they can be written out. I'm going to give you one example. If I do 236, this is in base 10, this is in decimal form. I can rewrite this as the powers of 10 in each of their places. So I can do 2 times 10 squared plus 3 times 10 to the first plus 6 times 10 to the 0 power. 10 squared is 100, 2 times 100 is 200. 3 times 10 is 3, 30. 3 and a 0. And then 6 times 10 to the 0 is just 6. 20 plus 30 plus 6 is 236. This is base 10 because these all have a base of 10. So if I was going to do a number like 523 in base 8, I would do exactly what I did here, but change the base to 8. So I would have 5 times 8 squared plus 2 times 8 to the first plus 3 times 8 to the power of 0. And if I calculate what that is, I will get 339. 64 times 5 is 320. Plus 16 is 336. Plus 3 is 339. So that's all well and good. I'll do one more example for you because base 16 is kind of weird. But if I have 2, B, 8, and E in base 16. So we use base 10 because there's 10 digits, right? 0 through 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 10 digits. Base 16 needs 16 digits. Well, they have 10, they have 0 through 9, but where do you go after 0 through 9? You still need 6 more. So what they opt to use is A, B, C, D, E, F. Those are 6 more digits for you, where A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So in base 16, goes up to 15 because 0 is included in the count, which makes it a 16. So I can do the same thing here. This one has 4 digits, so instead of my maximum being a power of 2, it's going to be a power of 3. So I can do 2 times 16 to the power of 3 plus B times 16 squared, but B was 11. So I'm going to do 11 times 16 to the power of 2. And then I'm going to add 8 times 16 to the power of 1. And then I have E, which was 14, plus 14 times 16 to the power of 0. And if I crunch these numbers, 16 cubed is 4096 times 2 is 8,192. Then I'm going to add 16 squared times 11 to that, which gives me 11,008. And then I'm going to add 8 times 16, which gives me 11,136 plus 14. I get 11,150 as the binary, or as the decimal representation of this base 16 number. I think that'll do it for converting back to decimal. How about I do one where I convert base 16 numbers to binary and binary to base 16 numbers, because I have a really cool trick for you. I copy and paste this in, format it a little bit. Okay. So these ones are really nice. There's a very simple way to do this, and it stems from a 4 bits being equivalent to the 16, right? Because you have 1, 2, 4, 8. There are 15 possible combinations here, plus 0, plus the no value. So there's 16 possible combinations here. So these 4 bits can represent 1 bit of hexadecimal, which is why hexadecimal is used. It only takes 1 digit in hexadecimal to represent 4 bits in decimal. But I'm going to use this unique relationship to very easily convert these numbers. So let's start with 7E0 in base 16 converted to a number in base 2. I'm going to switch pen now that we're on a different type of question here. So how can we go about this? I said there's a relationship of 4 bits per each digit in a base 16 number. So if there's 3 digits times 4, I'm going to write 12 zeros here. And then I just need to write the hexadecimal value and pair them with each 4 of these. So this first one's easy, it's 0. So it's just going to remain 0. The second one is E. And we said E was equal to 14, A is 10, B is 11, C is 12, D is 13, and E is 14. So how can I represent 14 with 4 bits? Well, I'll start with 8, then I'll go to 4, 8 plus 4 is 12, then I'll do 2 to get me to 14. And lastly, we just need 7. 7 can be represented as 4 plus 2 plus 1. And that's our answer. This is the binary representation of this hexadecimal number. You just pair up with each of the 4 bits. Super easy. Now let's do one from binary to hexadecimal. It's going to be exactly the same, just reversed. So this number is 1100 1001 0110 0000. That's in base 2, and I want to convert it to some number in base 16. Notice that I've already written this in 4 quartets, if you will. This last one's easy, it's just 0. This middle one is going to be 4 plus 2, which is 6. This one is going to be 8 plus 1, which is 9. And this one is 8 plus 4, which is 12. 12 was C. A is 10, B is 11, 12 is C. So this is C960 in hexadecimal format. I'll do it for these ones. Let's go to some more questions about numbers and their bases. Here we are with decimal values. So convert the following decimal values into the indicated base. Do you have any other pens here? This was a very nice pen from a friend of mine. It's a beautiful Japanese quality pen. It's Japanese, right? Yeah, it looks like it. Maybe not. Who knows? It's an Asian pen company. You can see that. Focus. Focus. Alright, anyway. So, let's do some conversion here. If I have 716 in base 5, how can I begin to do this? So, what you might be noticing is that modulus arithmetic and number bases are very similar to each other, right? for example, the face of a clock is in base 12 with no 0, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The second I go to 13 hours, if you're on a military base, 1300 o'clock, that's equal to 1 p.m. And what you're doing in your mind is you're doing a modulus 12. So it's very similar to this. In base 5, we just need to do a modulus 5 on this number. Let's do 716 mod 5. 700 is a multiple of 5. 15 is a multiple of 5. So my remainder is going to be 1 here. Now, to continue this pattern, we're going to do 716 div operator 5. And we need to ask ourselves, how many times does 5 go into 716? So we already know it goes 3 times from the 15. And then it goes in 20 times for each 100. So 20 times 7 is 140, plus 3 is 143. So that remainder is going to be, or not remainder, it divides into 716 143 times. And now, just like the Euler's formula, we're just going to substitute this 143 in as our new number while keeping the modulus 5, because we are still in base 5. So I'm going to do 143 mod 5. That's equal to 3. 140 is a multiple of 5 with a remainder of 3. I'm going to do 143 div 5. This is going to be equal to 20 plus 40. No, not plus 40. Plus 8. 8 times 5 is 40. 5 times 20 is 100. So 28. And now 28 is our new number. 28 mod 5 is equal to 3. 28 div 5 is equal to 5. Now 5 is our new number. We're going to do 5 mod 5. Oh, that's 0. I'm going to do 5 div 5, and that is equal to 1. 5 divides into 5 one time. So now 1 is our new number. 1 mod 5 is 1, and 1 div 5 is 0. And once we get to 0, we stop. Now we're going to look at the value of each mod operation. We only use the divs to get the next value, but we can look at the mod operation. So I have a 1 here, I have a 0 here, I have a 3 here, I have another 3, and then I have a 1. Notice that all of those are in base 5, and it makes sense. They have to be because we're doing modulus 5. So it's only going to be the digits 0 through 4 ever. If there were a 5, then it could go into the number again, and it would become a 0. And so now we can put these numbers together and get 716 in base 5. The order of which we got them in is actually the reverse order that they are given. So I'm going to start down here. My first digit's 1, and I'm going to the next digit. My next digit's 0. Then the next digit is 3. The next digit is 3, and then the last digit is 1. So this is 716 in base 5, and we can double check. We can say this place is 5 to the 0, this place is 5 to the 1, this place is 5 squared, this place is 5 cubed, and this place is 5 to the 4. So if I rewrite this, I can say 5 to the power of 4 plus 3 times 5 squared plus 3 times 5 to the power of 1 plus 1 times 5 to the power of 0. So let's calculate that. 5 to the power of 4 is 625. 3 times 5 squared is 75. So this is already 700. 3 times 5 is 15. 1 times 5 to the 0 is 1. So we have 700 plus 15 plus 1 is 716. So there we go. This is the process of converting any number to any base. We just do this mod div back and forth and plug that one back in. So I'm not going to bother going through the other ones because it's going to be exactly the same stuff. All right, for this next question, it looks like when I copy and paste, the formatting gets off, but just know all these second numbers are the exponents of the beginning numbers, and I'll write them out. But we want to answer the following questions about divisibility and modular arithmetic, and we may or may not have to use a calculator. But as you can see before, we had that 15 to the power of whatever super large number. There are properties within modular arithmetic that allow you to calculate uh, the remainders of these very, very large numbers without calculators. So let's find what is the remainder of 3 to the power of 50 when divided by 23. What's the remainder of this? Well, we can just use the modulus operator and do it that way. Now, we can't use the exact same property that we did before, where we did mod 23 of the base and then raise that to the power of 50, then did mod 23, because we just get back to this exact same equation again, right? 3 mod 23 is 3 to the power of 50 mod 23. It's the exact same thing. So what we can do instead is, I believe it's called binary expansion. We rewrite the exponent in terms of base 2. So I can say 50 is equal to, let's say I was trying to write it in base 2. I'm going to look at my binary numbers. It starts with 1, 2, 4, 8, 16, 32, 64, 128, right? So it's going to be less than 64 because 50 is less than 64. I can do 32. That would be 2 to the power of 5. So I'll do that. 2 to the power of 5 plus 32 plus 16 is 48, and that's still under 50. So I'm going to add 2 to the power of 4. That's 48, so I just have to add 2, and that's 2 to the power of 1. So as you can see here, 50 can be written as 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 1, because that's 2 plus 16 is 18, and 18 plus 32 is 50. Now, how does this help us solve this problem? Well, I can write 3 to the power of 50 as 3 to the power of 2 to the power of 5 times 3 to the power of 2 to the power of 4 times 3 to the power of 2 to the power of 1. And this is when I draw a diagram. I don't know what this process is called. But what I'll do is I have a value of n. What n is going to be is the value of the exponent that 2 is being raised to. And to denote that, I'll write my base to the power of 2 to the power of n. Oops. Power of n. And then lastly, I'm doing mod 23, so I have to keep that in mind. So I'm going to do mod 23. Now this is like a table of sorts that I'm doing. Let me draw this. So when n is 0, 3 to the power of 2 to the power of 0, well, that's just 3. 3 mod 23 is just 3. So that's the first iteration. Now I'm going to increase n by 1. Plug it in. I have 3 squared now, which is 9. 9 modulus 23, well, that's still 9. Now I'm going to increase n by 1. But what I can do is just use this value in place of the value that I was previously putting in, which was this. So I can do 9 squared is 81. 81 mod 23. Let's see what that is. Looks like it is going to be 12. And now I can use this number as my squared. I'm going to increase n by 1, square this bottom number, becomes 144. 144 modulus 23 is 6. Increase n by 1, square this bottom number, gets me 36. 36 mod 23, well, that is just 13. increase n by 1, square this bottom number. That gives me 169. 169 modulus 23 is 8. And now I could increase n by 1 again, but what was n originally representing? It was 3 to the 2 to the n. And in my representation, the maximum number was 5. So once I get to that maximum number, I'm done. So what did we say before? 350 mod 23. That can be rewritten in this term with 3 to the power of 50. So I can say 3 to the power of 2 to the power of 5 times 3 to the power of 2 to the power of 4 times 3 to the power of 2 to the power of 1. That mod 23. And then I can use the property that I introduced before where I can split this up. I can say 3 to the power of 2 to the power of 5 mod 23 times 3 to the power of 2 to the power of 4 mod 23 times 3 to the power of 2 to the power of 1 mod 23, and all that mod 23. So that's me rewriting it, but I already solved for what these three terms are. They're right here. So I just need to plug in those values, multiply them, and then take the modulus of 23 for that, and I'll get my answer. So let's plug that in. 3 to the 2 to the 5 mod 23, that was 8. This is signifying, what is it, mod 23? That's 8. Then I'm going to multiply by 3 to the power of 2, or 3 to the power of 2 to the power of 4 mod 23. That was 13. I'm going to multiply by 3 to the power of 2 to the power of 1 mod 23, and that was 9. And I'll do that mod 23. 8 times 9 is 72, times 13 is 936. And if I take 936 mod 23, I get 16. So through this process, we can find that 3 to the power of 50 mod 23 is equal to 16. This is a really large number. Some calculators might not even be able to, process numbers that large. Maybe this, because this isn't like ridiculously huge. But if you have like a 10-digit long number raised to the power of another 10-digit long number, you're going to need a pretty powerful computer to calculate that. So through this process, you can solve them mostly by hand. Let's do this mod 89. So let's do 5 to the power of 44 mod 89. Now the first thing I want to do is write 44, 5 to the power of 44 as its binary representation. So that's going to be 5 to the power of 2 to the power of 5 times 5 to the power of 2 to the power of, if we added 16, that'd be over, so we need to add 8, which is to the power of 3. So now I have 32 plus 8 is 40, and then I'm just going to do 5 to the power of 2 to the power of 2. So that's me rewriting 5 to the power of 44 in its binary representation, or in powers of 2. And so now that I have that, I'm going to create my table. I'm going to have my value of n. I'm going to have my 5 to the power of 2 to the power of n. I'm going to have my mod 89. And we'll start going. So this will just be 5 to start out with. Mod 89 is just 5. Then I'll increase n to 1. I square this bottom number, gets me 25. 25 mod 89 is just 25. Then I'm going to square 25. That gets me 625. Mod 89, that is 2. Then I'll do 2 squared, which is 4. Mod 89, well, that's just 4. And I'll do 4. 4 squared is 16. Mod 89 is just 16. Then I'll do 16 squared, which is 256. 256 mod 89 is 78. And luckily we're done. We don't have to square 78. So now we can plug these values in. We had a 5, a 3, and a 2. So I'm going to multiply the value of 5 times the value of 3 times the value of 2. So that's 2 times 4 times 78. Multiply those and take the mod of 89, and we will get our answer. 78 times 2 times 4 mod 89 is equal to 1. And if you don't have a calculator, what I just do is I find this product and then subtract 89 over and over and over again until the difference is less than 89, then I can subtract 89 without getting a negative. And the last one right before this was 90. 90 minus 89 is 1. So there we go. Nice, quick, and easy one. Let's move on. This is probably going to be the final question. This episode's getting a little long. So this is going to be dealing with decryption and encryption with the RSA encryption schemes. I'm going to switch back to the black pen because I feel like it shows up better on video. So there's some equations that you have to be aware of, and I'll write those down here. Okay, so I've written down a couple equations here that you will need to know for RSA encryption. Two prime numbers are chosen, Q and P. Those are given to us 23 and 29. To find our value of n, we multiply them. To find our value of phi, we subtract 1 from each and multiply them. Then we find the keys of the users. The first one is going to be noted by E, and that is found by finding the greatest common divisor between phi and E and have that set equal to 1. So we need to find some number that is relatively prime to phi. And then we find D, the other key, and D is just the multiplicative inverse of E mod phi. So let's start getting into this. We're given that P is equal to 23 and Q is equal to 29. So N will be equal to 23 times 29, which is equal to 667. And phi will be equal to 22 times 28, which is 616. 616. So that's A done already. I'm flying through this. Determine a valid value for E between 60 and 80. There is more than one possible value, so pick one for the next parts. So how did we do greatest common divisor before? Well, we took the digit and broke it down into its prime factorization. So if I factor 616, I get 2 cubed times 7 to the first power times 11 to the first power. Now I need to pick a value E, and we're given between 60 and 80. That shares no common factors. So I need to pick an odd number, definitely, so it doesn't share a 2. I need to pick not a multiple of 11 and not a multiple of 7. So it can't be 66 or 77. It can't be 62, 64, 68, so a bunch of those. Why don't we try, is 67 divisible by 7? All right, so I'm going to pick 67 as my E, because 67 factored, and it might just be prime. I don't know. I will need to check. Yeah, 67 is just prime, so it doesn't share any factors. Definitely doesn't share any factors. With the value of E found, determine the private key value D. So now we just need to find the multiplicative inverse, which is something we've done before. So let's go ahead with that. GCD of E comma phi. Phi is equal to 616 and E is equal to 67. So let's do that extended Euler's formula. Let's start with 616 minus 616 div 67 times 67. That is equal to, what is 616 divided by 67? Goes into 616 9 times. So 9 times 67 is 603. So we have 616 minus 603, which is 13. So now we can rewrite this equation using the 13. Let's make 67 minus 67 divided by 13 times 13. And that's going to be equal to how many times does 13 go into 67? Goes into it 5 times. 5 times 13 is 65. 67 minus 65 is 2. And we replace those, we get 13 minus 13 div 2 times 2. 2 goes into 13 6 times. 6 times 2 is 12. 13 minus 12 is 1. So this is proof already. Right, because I know the next one's going to be 0. I'll still do it for you. 2 minus 2 times 1 equals 0. Okay, there we go. So now let's solve this in our linear representation. Firstly, I'm going to simplify all these equations. We have 616 minus 9 times 67. And then I have 67 minus, what was it, 5? 5 times 13. And then I have 13 minus 6 times 2. So I'll substitute 2 into this equation, and I will get 13 minus 6 times 67 minus 5 times 13. That's me substituting in this equation for 2. I'm going to simplify this. I'm going to get 1 equals 13 minus 6 times 67 plus 30 times 13. Combining like terms, I get 31 times 13 whoops. Oh, this is in pen. 31 times 13 minus 6 times 67. I have an equation that can substitute 13 right here. So I'm going to plug that in. I have 1 equals 31 times 616 minus 9 times 67. Then I have minus 6 times 67. Let's distribute and then combine like terms. I'm going to get 31 times 616. 31 times 9 is 279. So this is negative 279 minus 6. Combining like terms gives me negative 285 times 67. And let's just double check that that is correct. 31 times 616 minus 285 times 67 is equal to 1. That is correct. So this is our linear combination. And the whole reason we did this is to find the multiplicative inverse, to find our public key, or our private key D. And the way we do that is we look at the coefficient of E. And what was E? E was 67. The coefficient is negative 285. We really don't want it to be negative. So we're going to do negative 285 mod 616. Luckily, this number is larger than this number, so I can just do that shortcut where I subtract it. And that gives me 331 as our private key. D is equal to 331, ladies and gentlemen. Now, using the values found in the previous parts, encrypt the message m equals 15. Give myself a new piece of paper here. I'm going to quickly rewrite what all our values are. All right, I have rewritten all the values we just calculated, and I included our encryption and decryption formulas. So notice, this is the D key that we just solved for, and this was the E key that we handpicked. And they have this interesting relationship where I can encrypt a message and get the cryptic message out, and then I can decrypt a message and get the original message out, given each key. So using the values found, encrypt the message M equals 15. So let's plug that into this one. We're solving for C. Let's do 15 raised to the power of 67 mod 667. How do we begin solving for this? Well, first we're going to take the binary representation of 67. I know that 64 will go in there, so 15 raised to the power of 67. That will equal 15 to the power of 2 to the power of 6 times, we just got 64, so now we need 3 more. So that's going to be 15 raised to the power of 2 raised to the power of 1 times 15 raised to the power of 2 raised to the power of 0. I have 1 plus 2 is 3 plus 64 is 67. So that is the binary expansion for you. Now I'm going to set up my table. And we're doing mod 667. That's an ugly number. Let's start with 0. 15 mod 667 is 15. 15 squared is 225. Am I correct in thinking that? I am. 225 modulus is still 225. So now we square 225 and get a large number. So I'm just going to write it as squared. That number modulus 667 is 600, believe it or not. Wow. Then we're going to square 600, get a large number. A large number that starts with a 36, by the way. Then I'm going to take the mod of that number, mod 667, and that gives me 487. Then I'm going to square 487. It gives me a large number. I'm going to do mod of 487 squared modulus 667, and I get 384. Let's square 384. I'm going to do 384 squared mod 667. I get 49. Got to do this one more time to get that n equals 6 value. 49 squared, now we're talking. This is like a much smaller number. 2,401 for 6. And that is 400. So now we have all our values. And now we can just multiply them out. So 400 matched up with this one. I have 400 times 2 to the 1. I matched up with this one. Times 225 times 15 matched up with this one. All that mod 667. So 400 times 225 times 15 mod 667. This is equal to 659. C equals 659. So that is the encryption. Now, for the sake of demonstration, I feel like I have to decrypt it now. Using this decryption one, and we can see it's going to be back and forth the same. So what we should get is M equals 15, by the way. So C is 659. 659 raised to the power of 331 mod 667. And I'm just going to go through this process and cut for you. So I've gone through that process, and now I can just plug these in. This is 558. This is 78. This is 165. This is 64. And this is 659. Let's multiply those all together. 659 times 64 times 165 times 78 times 558 is a large number. And let's take the modulus of that number, 667. And believe it or not, it's 15. I'll show on my calculator there if you can see. There you go. 15 right there. So that is how RSA encryption and decryption works, as well as how modular arithmetic in general, converting numbers of bases, all of the above. Thank you for watching. If you watched the whole thing, I commend you fully. That means you love math just as much as I do, or you just love the sound of my voice, or you hate one of them, but are willing to see it through to the end. All right, you have a great day here. Thanks for watching. Have a great day.